Welcome everyone to today's webinar hosted by Toradex in collaboration with our partner, Au-Zone Technologies. Our topic today is deploying artificial intelligence-powered spatial detection at the edge, lessons from real-world applications. We are thrilled to have you join us, and we have a really good session coming up with the real-life examples and really inspirational stuff. My name is Carlos Gonzalez, and I'm the head of partnerships at Toradex. It's my pleasure to introduce our main presenter today, Sebastian Taylor. He's the Vice President of Research and Development at Au-Zone Technologies, based out of Canada. Sebastian brings over 20 years of experience in embedded software design and development, with more than a decade dedicated to computer vision and machine learning at Au-Zone. Having spent years creating smart algorithms by hand, he's developed a very special appreciation for the power of machines that can teach themselves. So he really likes this AI trend, and in fact, a few years ago, it wasn't even called AI. So very thrilled to have him here and to speak to us. But before we dive in, just a few housekeeping notes. First, if you experience any technical issues, please let us know using the chat window on the platform. Then we will also have an interactive Q&A session at the end. You can type your questions in the chat window at any time, and at the end I'll read them out during our Q&A. And just for you to know, this webinar is being recorded and it will be available on demand for you. So there's no need for you to take in screenshots of your favorite slides. We'll send this over to you guys. All right, so here's what we have ahead of us today. We'll start with a very brief introduction to Toradex and our collaboration with Au-Zone. I will then hand it over to Sebastian, who will share a very inspirational real-world deployment, the ocean cleanup, and how the technology is helping fight ocean pollution. He will also dive a bit deeper into their own platform. So that is the HAI computer vision and spatial detection platform, and how they leverage the Toradex embedded computing technologies. He's going to be also providing some insights and metrics from building ADIS, which is this automated debris monitoring system that they have and they developed for this particular customer. And then Sebastian will give us some information about how they go about monitoring and sending updates to these devices that are in the middle of the sea. And as I said before, we're going to finish with a brief Q&A. So please do keep your questions coming. But before we get started with this great topic of the ocean cleanup, just a couple of words about what Toradex does. So as you may know, we are a Swiss-based embedded computing company. We offer ARM system of modules, but not only that, we also offer carrier boards, custom solutions, and connectivity. When it comes to our SOMs, our system of modules, they are famous because of their reliability, the long-term maintenance, and also the fact that they are very scalable. So as you may know, with a SOM, you have a faster time to market with a reduced development risk. Essentially, they just make your whole development faster and easier. In addition to SOMs, we also have off-the-shelf carrier boards, either for development purposes or basically for volume production. We offer the design files so you can customize them for your own project. But since recently, we also have a custom solution, so we can offer you customization services and adapt your carrier board to your needs. And offer the end product, so the enclosure and even the end product. Last but not least, we also offer an IoT platform called Horizon, which is very critical for this specific use case of this webinar. It provides over-the-air updates, cybersecurity capabilities. It is a very critical part of this. And we'll get into a bit more detail later on in this presentation. Also, just maybe a couple of words about the partnership between Toradex and Au-Zone. So partnerships are central to our strategy. As you know, we provide the hardware and the software foundation, but building a complete embedded system requires a very strong ecosystem and a lot of different connecting pieces. So our collaborations include technology integrations, joint marketing efforts, roadmap sharing. So we work very closely with our partners to make sure that when the customers come to us, they have basically the back and that we can walk them through the whole project. And that's the case actually with Au-Zone. You will hear about a specific customer, and that's the way we like to collaborate, to have this very deep technical integration to ensure that the customer actually has everything covered by this partnership. Also, just so you know, both Toradex and Au-Zone are very strong NXP partners, and we have a very deep expertise on the NXP platforms. And now, without further ado, I'll hand it over to Sebastian to tell us a bit more about the 3D spatial perception technology. So Sebastian, over to you.
Thank you. With Au-Zone Technology and our primary offering, we call it EdgeFirst AI, and this covers platforms, the perception stacks of the software running on the platforms, data sets and dataset tooling for capturing data sets on these platforms or other types of platforms. And then finally, EdgeFirst Studio, which is a cloud-based platform for dataset management, MLOps, training models to deploy back to the device. So today we're going to talk about how we used this stack to develop the ADAS platform. So to start, I'm going to play this video here. This was put together by the Ocean Cleanup and gives great background about the project, what they're trying to achieve, and why the ADAS platform is important. The video is about 4 minutes long, so I'll let it play, and then we'll dive into how we built it under the hood.
Thousands of ships move around the world's oceans all day, every day. So we thought, how do we convert some of them into a research fleet with the help of AI? Plastic pollution is one of the biggest threats our oceans face today, and our mission is to clean it up. In order to solve a problem this big, we must understand it on a global scale.
For us at the Ocean Cleanup, data is key. And specifically for the Ocean project, it will help us to increase the effectiveness of our operations. We've been successful thus far with harvesting large amounts of plastic. The next step for us is to make sure we operate in those areas where the plastic density is the highest, the so-called hotspots.
And that's why we have our very own research team. In the past, this team has made a huge effort to cross oceans with vessels and even an airplane to take plastic samples and gather data. In 2016, they went on an aerial expedition to the Great Pacific Garbage Patch,
which taught us that imagery can be a really good tool to gather data on large floating plastics. However, it was only on one flight and it's not very scalable. And this got us thinking, how can we use technology to gather this kind of data at an even larger scale?
And that's how ADAS was born. ADAS stands for Automated Debris Imaging System.
It's an intelligent camera system that uses AI on board. It's a very easy system to install on any ship, and it's also highly robust.
In order to fulfill its purpose, ADAS needs to be out on the ocean as much as possible, and nothing sees more of the ocean than ships. With ADAS on board, vessels become part of a massive research network, helping to expand global coverage of plastic pollution studies. That's why it's a very collaborative project. The first step is finding a vessel of opportunity, and that's where our partners play a crucial role.
Today we're at Glovis Sunlight vessel, and this is one of Hyundai's Glovis ships. They have been a key partner in getting us the ships of opportunity required for ADAS. And today we're installing an extra unit of this latest generation ADAS.
Hyundai Glovis has supported this effort since 2023, as ADAS installation is a core project of our partnership. The camera's GPS ensures that it turns on automatically only once the ship is no longer in an exclusive economic zone. So, once the vessel is offshore, ADAS gets to work by capturing and processing images. The integrated AI identifies plastic waste in the water and, to save space, retains only the relevant parts of the image. When the vessel is close to shore, it transmits the data to the ATIS database. From there, specialized software combines all collected data and maps it, generating the ATIS Data Visualization Map. To get to this version, Robin and his team first had to build a proof of concept using GoPros. Along with the expertise of Au-Zone Technologies, they improved it towards the current version, ATIS 2. ATIS is so groundbreaking that it's part of the United Nations Ocean Decade, as it offers a low-cost solution to monitor and digitally represent plastic debris concentrations in the ocean.
ATIS collects data continuously, and that allows us to build trends and to look into patterns through seasons, but even through years. And this allows us to see if cleanup efforts or cleanup policies have an effect.
The best part is that this data will be available open source for everyone to use in the coming years. This is one of the many ways we are tackling this global crisis that requires urgent action. Plastic pollution is increasingly harming wildlife and ecosystems, and we need to do something about it. Find out more about our mission on our website. And tell us in the comments, how would you use AI to accelerate our impact?
Okay. All right. So, how was it built? Right. So the platform. So we'll go through the 4 core blocks and how we used it to implement the ATIS, as well as some kind of insights on the ATIS platform itself. As well, importantly, is how we leveraged Horizon OTA to collect data out at sea, as well as push updates back to the devices. So starting with platforms, so we develop sort of 2 main categories of platforms. They're all based on the same core system, which is the Maven. It's a camera vision-based platform. It's got a 4K, so 8 megapixel camera. All the compute is on board. It's based on a Verdon IMX8M Plus for the core compute. We'll dig more into capabilities under the hood. We also develop a platform called Raven. So we start with the Maven and add a radar module integrated into it as well. We see it in the middle there. And with that, we develop camera plus radar fusion. So we have low-level fusion models that consume the raw radar data cube and merge this with the camera. This is very useful for scenarios where you might have degraded optics, smoke, fog, nighttime, or if you just need really precise ranging and velocity information. The Raven HD is just an expanded version of it. You can see it on the far right side. So it has a much higher resolution radar. It basically doubles the transmitters and receivers on it to really give a better 4D signal. So I guess we were going to do a poll now on what types of sensor platforms are you considering for your next AI application. So monocular camera means a standard camera, not stereo.
Right, so it seems quite even, the results.
Yeah. Okay, lots of people with LiDAR as well.
Yeah, I'm actually surprised about the radar and LiDAR, but I would expect more cameras, more normal traditional cameras. But that's great to know. People are experimenting.
Yeah, LiDAR is very interesting too. It goes from very low cost, sort of one vertical line all the way. Here we got a Ooster depicted here on the screen. They, well, I guess we're not on that screen right now, but it's a fairly high-end LiDAR platform. So incidentally, that LiDAR platform, so something like an Ooster, is capable to be connected to the Maven, to IMX8M Plus in general, and real-time processing and fusion with that system, which is a whole other interesting topic, but not what we'll be covering today. Right, so moving along, the Maven, as I mentioned, is this is what ADIS is built on. So we show here the simplified different front enclosure. It's a little bit more under the hood. I guess predominantly the LTE modem, and then the customized software stack specific to ADIS. A little bit more on ADIS. So as you saw in the video, simple installation is pretty key. Somebody needs to be able to mount this on a ship anywhere in the world with no expertise on cameras or certainly AI. So it's really mounted, apply power, and go. Everything else we can manage remotely over the LTE when there's connection. This platform lives basically at sea. It's pretty harsh environment, salt water, can be very tricky to deal with. So the Maven camera is tested to IP67. It's been sailing for a few years now, ensuring robustness to this type of environment. And then low power is pretty important as well. It gives us passive cooling, as well as just generally making it easier to install in different places. And it does follow safety certification in terms of reducing fire hazards and risk of electrocution. Under the hood, we see it's built on the Verdon IMX 8M Plus SOM. So this gives us a few key pieces. ISP, we're running the camera at full 4K, 8 megapixel. As we'll see later, that's very important to be able to detect quite small debris. The MPU, again, critical for this type of application. We've got a detection model that's operating at that full 4K resolution. It just that absolutely requires an accelerator to work. And then extended temperature range and long-term availability. This product will be deployed for probably a decade or potentially more, sailing the seas and monitoring debris.
So maybe a question before we jump in the poll. So the hardware platform, I mean, this one is the customized version for the ocean cleanup, but the ones that you showed before, the Maven, the Raven, so these are generic. And are they supposed to be for development purposes, or is that something that people use on production as well?
Yeah, so it's a good question. Obviously, in the case of ADIS, these are deployed as a product. So we manufacture them right here in Calgary, final assembly, and then ship them out to be installed. So that's an example that's turnkey. It's a product, but it's fairly low volume. When we're looking for higher volume applications, typically we'd be partnering with a company like we did with Ocean Cleanup, where there'll potentially be some customization and whatnot of the product. So the Maven platform serves as a an IP67 ready to install, ready to start developing in the real world today platform, but it is ultimately a development platform. At least some minimal software for the business case needs to be developed on top of the perception stack to fulfill the needs of the product, and then maybe that form factor works as is and it's ready to be scaled up and deployed like that, or there's some customization, all the way so far as our software stack can be deployed on completely custom solutions. So a customer that's developed their own hardware, our software stack goes onto that.
Got it. Yeah, I think it's a good point that this is a specific example of maritime mapping, but this platform could be actually applied to pretty much any vertical, like from agriculture to off-road to anything really.
Yeah, robotics. Yeah. Touch a little bit on it, but the software stack is developed sort of like a robotic type framework.
Sounds good. Thanks.
Right, so we were going to do a quick poll on the type of platform you're considering for your next AI application. So NXP IMX would be anything from 8M plus, IMX 93, the upcoming IMX 95, and so on.
I'm very curious about the results of this one.
Mm-hmm.
And by the way, if you are using other, feel free to add it to the chat if you feel comfortable with it.
Yeah, good.
Right? I'm not surprised actually.
Yeah.
This kind of it's meeting my expectations.
Bit of a targeted audience, of course. But,
yeah, but it's good to see actually NVIDIA showing up there, because I think what you have is an interesting solution to address some of the challenges that NVIDIA users face out on the ground, right?
Yeah, we see a lot of NVIDIA, obviously the Gorilla. And something we spent a lot of time on is just showing that path to, if you started on NVIDIA, whether desktop or, Jetson, how to migrate that down to, a low power platform like the 8M plus. As we'll see here, it's capable of some pretty state-of-the-art applications, but, it's 2 tops versus 30, 60 tops and above on the Jetson. So there is some work to make that happen. So moving on, we'll cover the perception stack. So as I mentioned before, it's kind of built as a ROS-like platform. We use Zeno for the communication subsystem. There's a number of services that each provide a certain service, communication over Zeno using the same CDR encoding as ROS2. So this can plug into ROS. You can work with standard ROS tooling like RViz and Foxglove for visualization. Recording data sets or just what the device is doing at any given time can be done into an MCAP file that all the recording infrastructure is in place on the device, and it'll record all the sensors, localization, perception output and whatnot, and then again can be used in standard tooling for that. The sensor support, so camera obviously is supported, as well as radar and LiDAR. The communication exchange we have optimized, so the camera buffers are all being exchanged over DMA. So a platform like this, you can't pack a full frame, certainly not a 4K frame over standard messaging. So by being able to just pass DMA handles over the center of communication, we can really optimize that stack. And then, of course, GPS, IMU for something like ADAS is quite important. And then finally, the customer just develops their custom applications by subscribing to relevant topics and performing actions on it. In the case of ADAS, actions are logging. There's an SQL-like database where we log all the events, where all the debris and other types of objects that we detect, where they are, time of day, things like that. And then when it eventually gets to port, we're able to synchronize over LTE into an ocean-specific database. We saw that in the video, that data set that they're building, that they plan to open source in terms of where all the debris is in the world over time. To develop this type of system, so I've talked about the optimizations required. The model is running at full 4K, so it's roughly 4,000 pixels by 2,000 pixels that needs to be captured and input into the NPU for the model to run. So this is something we've spent a lot of time optimizing, not just for 4K in general, but in the 4K space, it is quite important. In this chart specifically, we're showing, so typically a model, you'll train it for RGB. You open an image, you get RGB pixels. That's how you train the model. That's how you deploy it. So in our case, on the 8M Plus, there's a 2D GPU, which can be used for converting from the camera's YUIV format into RGBA. In this case, the 2D GPU just outputs RGBA. So typically you then need to remove the alpha channel before copying it to the NPU for processing. When dealing at more, let's say, normal resolutions for models, there's still a measurable impact. Time is important, but as we scale up the resolution, that time goes high and high. So that's that blue line that you see. So one first improvement is training the model for RGBA. Technically, the model doesn't actually need to be retrained for that. We can insert just a RGBA, like a slice operation, to remove the alpha channel. And we see that drastically cuts down the input time of the input. To take it a step further, we can actually train the model natively in YUYV so that the model is trained for the same format that the camera outputs in the first place. And that yields the best input time. The DMA buffer output from Video for Linux can be used directly by the NPUs, drastically cutting input processing time. On the model processing time, we see that, adding that RGBA slice, it's not expensive, but it does take some time. It's not zero time. So it increases ever so slightly the timing, but compared to the previous slide, the reduction in input processing time is still greatly beneficial. And again, YUYV gives, in this case, the best possible performance. The model on its own is slightly faster than the RGB or RGBA models, and the input time is greatly faster. Now, this does require retraining. The first layer of the model is getting, a YUV image rather than an RGB image. But otherwise, the model doesn't care, if you will, what pixel format is being used, as long as the data set's trained like that. So to do this, we have basically it's a camera adapter class. Think of it as an extra step to the image augmentation pipeline when training a model, and it's an augmentation function that runs all the time. So it's not randomly selected. It always runs as the last step of augmentation, and it'll present the image the way the camera will present the image on the system. So whether that's RGBA, YUYV, NV12, or so on. Next, so that was running the model. Object tracking is pretty important. So this here is an image. There is debris in it. There's also some waves, and it's really, I've seen this video before. I still can't tell the difference. So I'll play it quickly. You can see there's the hard plastic being detected and tracked. So we still see it there on the last frame. So it's, it's challenging to see, and you see other speckles on the screen that, might look similar, but they're just, waves or sea foam, things like that. Early on in the project, we really struggled with that, wave crests and other just sort of, water artifacting, causing false positives, but it moves very differently than the plastic debris. So the tracking gives us, a number of useful things beyond it, but also really help reduce the rate of false positives, because if we're able to track the object and certain parameters that expect the tracks to move in a certain way, it reinforces detections. It also allows us to distinguish, different debris, so we can say, over a given time frame, how much unique debris was observed. Since we track it, every time we see a piece of debris, it gets a unique ID, and it doesn't get counted multiple times. Oops, that's just the video again. The tracker is quite high performance. In that case, there was one piece of debris, but we show scaling across number of boxes or number of potential objects to track. Even when we get into 100 objects in any given scene, the processing time is under 3 milliseconds, under 3,000 microseconds for doing the track processing. So this is a really useful algorithm to have added to the detection. It's based on the bike track algorithm, so it gets all the raw bounding boxes. So it also allows us to see objects that maybe you normally wouldn't get after NMS, because the tracking happens before that. It gets more candidates, and if it's an object that it's already tracking, it allows a lower detection threshold to be accepted as being part of that track. Next, we need to localize the debris. So for that, there's a homography transformation where, given knowledge of the camera's pose and the height from the water and a known plane. Now, the ocean is not exactly flat, but for the purpose of this, it's sort of flat enough for the type of estimates we need to be able to produce. The camera's pose is captured from the IMU, as well as when we can find the horizon, we actually use the horizon as a way to calibrate and improve the IMU's prediction, and basically just improve the camera's pose. Height off water is a parameter. It's basically where it's mounted on the ship. And it tends to be fairly consistent. The difference being if the ship is loaded or unloaded. And then this information can be used to generate this type of data. So this was a plot. This is what was referred to in the ATIS video. So this is a dashboard specific to ocean that is measuring where debris is being seen and density based on missions. And they're building this up where eventually it'll be a map covering basically all shipping lanes that have ATIS deployed onto them. So this is an example of kind of the cloud dashboard that they're using for consuming the end data. There's also a web interface on the device. So that's part of all the Maven cameras, but it can be skinned and customized for customer specific applications. So in the case of ATIS and the ocean cleanup, the web interface is customized for sort of ship specific details as well as application specific parameters, like the geofence. It mentioned only recording outside of economic exclusivity zones. So that's part of the parameters that can be configured on the device. Can be configured remotely as well, but when installing the device, you can plug in a laptop or use a phone or whatnot, pull up the web interface and configure some of these parameters. So that was the perception stack. Now we'll look into the data set a little bit more. So as we saw, the debris is quite small. And that's why the images need to be recorded at 4K. We need enough pixels to reasonably make a detection. There are limits, right? We can't tell debris from 1 pixel. The data set, I believe we're limiting it to an object that's at least 10 by 10 pixels. But even that is pretty challenging. You can think of something like Safar, where you're detecting planes, cars, and whatnot at 32 by 32 pixels. That works pretty well, but that's classification. We need to do that across roughly 4,000 by 2,000 pixels. You'll also notice the images are portrait mode instead of the standard landscape. The sensor can be mounted in either orientation, portrait or landscape, within the Maven unit. And for ATIS, it's mounted portrait, just so we get more of that field of view. The ships, as they sail, the image is going to move to the left or to the right. So we want more vertical field of view, so we can see more of the water and have a better chance of seeing that horizon that I mentioned was important for helping improve the pose estimation of the camera. When Ocean first started with camera, well, not with cameras in the plane, but with the GoPros, they built an initial data set. So we're able to use that to kind of start the experiment on ADIS and adapt it. You know, this camera is a little bit lower resolution than the GoPro, has different, you know, optics and whatnot. So showing that we could still get good detections, that, you know, the ISP could provide good processing of the image to avoid, you know, different artifacting, chromatic aberrations, things like that. You see the image on the right here, you know, that's looking into the sunrise, sure. But, you know, that's a difficult image, and still, you know, it found the hard plastic there. These are examples.
Question, Sebastian, how much of an issue is the fact that the debris moves? Because basically, when you are mapping this debris, you capture it at a given time and location, but it may actually move the next day or the next hour.
You like in general movement, that's fine. Yeah. So the goal of ADIS is to kind of map the, you know, to provide like location, but really it's about density, like measuring density of plastic when the ship sailed. So we know where and when the ship was, and, you know, how much and the type of debris it was seeing. And that's, you know, the processing that Ocean does on it is when they collect from many devices, all this information, it becomes more of a model of, you know, the world of where the debris is and going. So, you know, ships probably not going to pass in exactly the same place, but they do have models of ocean currents. They have a general idea of, you know, how things move, and basically they combine all that with what ADIS is seeing, what, you know, they know about other observations, like we know where the garbage, Pacific garbage patch is.
Okay.
So yeah, it's basically a large, you know, statistical model of the world, but they do need you know, eyes on the ground, if you will, and that's what ADIS provides.
Got it.
Yeah, again, this is just examples of the crop. So when we make a detection, we'll crop out the bounding box and store that into the database as well, so that it could potentially be transmitted back to the cloud when time permits. And this is used for basically auditing. People do go and review what's being seen. It's a long process, but it helps us get a sense of how well the system is behaving. So, you know, what we hope to see is all the crops have, you know, clear, identifiable objects that are known. Yeah. So this was from last year. I don't have a map of this year yet, but basically as of October last year, that's kind of where I guess some of the ships were being put up for storage in the winter, and we looked at where all the data was collected. So this is the sailing maps and where data is collected. So each dot represents some, you know, amount of data that was collected. The coloring is basically different vessels, different journeys. You can see there's little gaps in between, and that's from, you know, given the GPS, we know, you know, what sunrise and sunset is at any given place on the planet, and we use that to stop collecting data at nighttime when we're not going to be able to see anything. So yeah, it gives you a view of that. Not sure what happened at the Suez there. Maybe that ship was stuck and it had to turn around and take a different path. So now we've covered the platforms, the perception stack, data sets. We'll see a little bit about EdgeFirst Studio, platform for collecting, managing data sets, training models for deployment. So it's a cloud-based platform. Workflow covers data curation, so data set management, annotation, training, validation, and deployment of the models. It covers different types of use case tasks for image processing. So 2D bounding boxes, 3D bounding boxes, depth maps, semantic segmentation, instance segmentation, object tracking. It works with cameras, of course, but also radar and LiDAR. So it's able to train fusion models or traditional models that do kind of late fusion, where the radar and LiDAR is used to give you good 3D bounding boxes, for example. It's an example of some of the visualizations. So we see, a typical bounding box around what's hard plastic in this case, the segmentation mask, the polygon around it, the different types of debris classes, the mapping. See a little video of that later. So for any given image in the data set, we can see exactly where in the world it was captured. Useful for ocean, but useful for all sorts of applications. If you just want to know, where data came from, I mean, that is pretty invaluable. On the bottom left, you see this is being combined with LiDAR and 3D view and showing the 3D bounding boxes. So this is just a little short video, but it just shows, as I mentioned, the location-aware data sets. So all the data, we see like the day-night gaps there, and then all the data we've collected, you can narrow down your search like this. So from a given sample, it can show you where it was captured, but also if you want to just see, like, I want all images that were collected in the Great Pacific Garbage Patch, you can kind of set a search area and just be like, okay, give me all the annotations that are in this region of the world. And then for model training, so the when it was originally started with the GoPro, we trained a YOLO V5 model on a desktop, and it's basically just to prove that, yeah, it could make detections, it could run at high resolutions and give meaningful results. And then from there, as part of getting this ported to ADIS, there was first a evaluation done. Model pack is basically a EdgeFirst optimized flavor of YOLO. So it's very, very similar to typical YOLO architectures, but where we've tweaked and optimized it for int8 processing on low TOPS platforms, kind of like the IMAX 8M Plus. So for ADIS, for ocean type data set, in this case, we had a minor improvement in MAP. It's largely the same, but about 1% improvement. But the big one is the 4 times faster than YOLO V5. And that also combined with just supporting very high resolution non-square images can be something that's challenging with those models. Now, this is very data set specific. If you were to look at our COCO numbers, they're probably over 10 percentage points lower than YOLO V5. So it's not that this model is just magically 4 times faster, but most AI deployments aren't COCO. They're more narrow in scope. COCO has all sorts of different contexts, different environments, different types of objects. For ocean, we've it's up to 20 classes, I believe, in the data set, where they're really trying to fine tune different types of debris, and it's all in the ocean. So and we obviously spent more time hyperparameter tuning than YOLO has on ocean, but it just goes to show that a model can be, I talked about going from NVIDIA to 2 TOPS. How do you deal with that big change? well, often a model that's just really optimized for that type of platform, even if it doesn't have the same COCO metrics on a more narrow application. And narrow doesn't need to be ocean, like people detection, car detection, on the roadway, they're all kind of similar. Where if we do, the Berkeley driving comparison, our scores are much closer. I think in some cases higher than the YOLO V5 on something like that, where you're detecting cars and people on the road, compared to COCO, where it's just sort of all over the place. So now we'll talk about how we manage ADAS deployments and how we work with Horizon OTA. So first, this is just a map showing shipping lanes over the world. Basically, this is the target environment for ADAS. This is where ADAS will be deployed. Maybe not all the shipping lanes, but it gives you an idea of where the system operates, where it does all its work. By contrast, this is a 5G map, but it shows, there's where you have cellular connectivity in the world. No surprise, it's on land. There is no, LTE coverage out at sea. So the device is largely offline. It's offline almost the entirety of its life. It gets to port. It hopefully can get connectivity in port, though you'd be surprised that sometimes that's not as apparent. And then it's back out to sea. So we need to be able to cache everything it sees to the device, and then in the small window of opportunity, publish all the metadata metrics, the crops, health metrics of the device, make sure it's running as expected, pull down firmware updates, potentially model updates, and things like that. So while it's offline most of the time, and when it is online, the connectivity is quite poor. Eventually, logs do make it to the cloud, and eventually updates do make it to the device. So with that, I'm going to ask Carlos to talk a little bit about Horizon OTA, and then I'll talk a little bit more about how we use it on Maven ADAS specifically.
Yeah, thanks, Sebastian, for the great lead-in. So since Horizon is such an essential part of the solution, let me just take a moment to explain a little bit more in detail. So Horizon is both an operating system and an IoT platform. So from the bottom you can see hardware. So it is an embedded Linux solution. It's a Yocto distribution, which is open source and is free to use, and it works actually great on the Toradex hardware, but it can also be run on third-party hardware. So ST, Raspberry Pi, RISC-V, x85, 86, sorry, pretty much anything. It's basically an operating system that you can run on anything Linux based. Then on top of that, we have this great solution based on Docker containers. So it is optional, and in fact, the team at Au-Zone for this specific deployment, they are not using containers. They use the Horizon Core Builder to integrate the application directly on the Yocto build. But you can have containers to essentially isolate all the different applications and to expedite the deployment. We use FluentBit for device monitoring, Actualizer for update management, OS3. So it is a modern operating system. And then you can see on the top the Horizon Cloud, which is this full IoT platform that you use. And in fact, the team at Ocean Cleanup use for device monitoring, for offline and online updates, for security management. And it has an API as well. So you can use the API to connect to your own cloud or even to customize the interface. So essentially, I just wanted to actually provide a bit of an overview of how you can actually abstract Horizon to your own project. But this use case is actually a great example of how to make the most of it. So yeah, Sebastian will give you a bit more of a background on how the team is using it.
Thank you. Yeah, so as Carlos mentioned, update mechanism is important. Ultimately, you will need to deploy firmware updates. And there's a piece of OS tree and used by Horizon OTA for delta updates. So a delta can be generated from version 1 to version 2 and so on, and only what's changed, even within a binary, is transmitted to the device. So this here shows some benchmarks that Toradex did to compare different types of update mechanisms, and we see kind of the same type of thing. Our updates are quite small on the system because it's all basically just the delta from version to version being deployed. So yeah, I guess we had a poll here on how are you planning to manage firmware updates. So Horizon OTA, Mender, fairly common one. Ubuntu would be in the case where you're using Ubuntu on your device, using the standard update mechanisms there, or it can be other distribution, something custom, or if you're using something else entirely, please share it in chat.
Yeah, I can see already some results coming in. I think it's going to be interesting to see the results. Maybe custom will not give us much. So, but yeah, I think it's also interesting to see if people are building their own update solution. Here we go.
Yeah, a lot of custom.
Yeah. Yeah, I mean, but Horizon, obviously the audience, it may be a bit biased, but it's good to know that, about 1/3 of the people know about Horizon. So
yeah,
it's good to know.
I'd be curious on custom, if people are fully custom building from the ground up, or, building on top of something like OS tree and whatnot. Okay.
Good.
Right. So as you mentioned, the Horizon OTA dashboard is being used for ocean cleanup as well. So we've got different types of deployments. We saw the Globus ships. There's the research vessels run by ocean cleanup. So these are all separated into different fleets. So we can monitor different fleets and drill down to specific devices. We can remote into it, though. So for the research fleets, they do have Starlink. So we can basically SSH into a device that's in the middle of the ocean, and that works very, very well. But for the more like actual production deployments that's on these vessels, there's only LTE connectivity. Import sometimes it's quite unreliable. So remote SSH is not really feasible, but the rest of the mechanisms, doing firmware updates, the model deployments, and collecting just metrics of the device, health metrics, and the database synchronization works quite well. So for model updates, we use a feature called the subsystems in the Horizon OTA. So this can be used, in fact, the examples provided by Horizon are think firmware for a microcontroller that might be on your device. So if you want to deploy new firmware to a micro, it's not really part of your core VSP. That can be done through subsystem and handle flashing the firmware update. In our case, we have a model manager that integrates with the subsystem updates. So it receives a new model, it verifies, it's technically the subsystem framework, verifies checksums and all that. And when the model's ready to be deployed, it puts it at the right storage location and updates the model service to now use this new model. So from the dashboard, we can know, which device has which model, how much coverage a model update has across the whole fleet. Since these devices are largely offline most of the time, firmware model updates, could take, 6 weeks to fully propagate across the fleet. But we get, to see all that status from Horizon OTA. Fleet monitoring as well. So the core metadata in terms of where we're seeing debris. That uses a separate channel where we're synchronizing the SQL database into the Ocean cloud platform, and that's sort of what's used by their researchers for modeling debris in the ocean. But we still need to monitor health metrics. So health metrics are, how's the device operating, temperature, storage capacity, but we also monitor the health of that other synchronization method. The way it works, prioritize pure metadata. Once that's been synchronized, then they'll start uploading the crops. But managing that with limited connectivity can be a challenge. Updates that we pull down with Horizon OTA, I mean, that basically just worked out of the box. There was no real optimization needed there. But modems tend to have better download than upload, and also the updates are quite small. We're using the Delta updates. The entire BSP compressed is under 200 megs for ATIS. We've kept it very, very small. So updates are not really a problem, but the metadata upload does add up, especially if the ship's out for weeks and weeks at a time. So early on, we were having issues where basically we were recording more than we can upload. The devices would just never catch up. So with optimization of the data channel and how minimizing what we need to synchronize, that was greatly improved. But that's something that we need to monitor across the fleet, is how well they're synchronizing what they're seeing. Just a little video showing visualization of the metrics on the web interface. So finally, this is the same timing chart we saw before. I just bring it up to talk about it a little bit. So in the case of ATIS, again, we're running at the model at 4K. If you look at the times, it takes about a half a second to run that model. So effectively, we get roughly 2 frames per second. Now, debris doesn't move, that quickly. And so 2 frames per second does give us, enough throughput that we can track objects. So for this use case, that's appropriate. But for other use cases, maybe you need more performance, maybe you need higher resolution. More likely you need faster performance, or even at the lower resolutions here, you need still even faster performance. And for that, we do support various AI accelerators. So that can bring your processing closer to and beyond some Jetson platforms. So as an example, Jetson Xavier is 32 tops. The Canara accelerator is 42 tops. So it can give you really that extra horsepower for applications that just need it. Either you're running multiple models, or the models need to run at higher resolution, or they're just higher complexity models. The accelerators, there's an M.2 connector in Maven or Raven, so that accelerator plugs in and it fully integrates with the perception stack, the middleware stack, as well as EdgeFirst Studio, so we can train sort of the heavier duty models and deploy them to the device and run them on that accelerator platform. So that's it for today. If you're interested in more of our perception modules or EdgeFirst Studio, on the right side, you can click the link, and there's free trials of EdgeFirst Studio where you can import data sets, annotate them, train models to deploy to these NXP IMX type platforms. And on the left side, the EdgeFirst modules between Maven or Raven. With that, we're ready for Q&A.
Great, Sebastian, thank you so much for this very interesting presentation. So we did actually get a few questions, so I'll just go through them. So one is about, so the question is, how does this model do the edge detection better, faster than traditional adaptive algorithms for edge and image processing? So it's, I guess, comparing AI with adaptive algorithms for
Yeah.
edge.
Well, that's a good question. How they evaluate, like in our case, the customer did the evaluation using, an AI-based detection model, so the YOLO model. So we can comment on how it does better, especially faster, to fit it on the edge platform. But compared to other, if I were to use face recognition as an example, where those used to be developed without using AI models with more feature engineering, they worked very well. The AI models work better, but more importantly, the time to craft them, to do to prepare them for deployment is just drastically lower now. There's not, typically you don't need to tweak your model for your data set very much. You'll need to tweak your model for your platform, for the device you want to deploy that as more of a optimization, but across different data sets, not so much. The work you do is very generalized. I don't know if that helps answer the question. But...
Yeah. I mean, I guess maybe you can focus on the fun things. So it kind of got rid of a bit of the tedious work. With the AI, you can.
It really brings it. It's more of a data problem now. We show the ocean data set. That's not really something that we're doing at Au-Zone. Like, we've done a little bit of work with it and supporting the ocean, but really, they're the ones who know, what's debris. Like today, I could open all sorts of images and I might not even know that there is debris in it or what the type of debris. So it's really important to be able to keep that in the hands of the domain experts. And these types of models just means that the domain experts focus on, what they're looking for. And the AI perception people focus on just making sure that those models train and deploy well to edge devices.
So we actually have a real-time follow-up question on that. So do you have any benchmarks on this model pack versus other algorithms?
Yep. So those can be shared. Some of them are available on our documentation site. So doc.edgefirst.ai. There's a whole section talking about the model, how it can be trained, and some performance characteristics. And of course, you can sign up for a free trial and go test it out on your own data set or some of the reference data sets, such as COCO or BDD or whatnot.
Yeah, that does. I have to say that you have great documentation on your website, so it's definitely worth having a look. All right.
So, just one last little point, I guess. So I mentioned the performance. So yeah, compared to say the YOLO, like the Ultralytics YOLO V5, 8, and so on, it's kind of in the 2 to 4x faster. And then the MAP, it's totally data set dependent. So, on COCO, there's a pretty big drop in accuracy for whatever reason. But on the more focused data sets like Ocean or BDD, they're very close.
And we'll include links to the documentation when we send the PDF with the presentation, so you can look at that a bit more closely. All right, another question is for the ocean cleanup specifically, does the Maven use AI acceleration hardware or just the built-in NPU from the Virgin?
Just the built-in NPU, yeah. So that 2 frame per second metric, that's using the built-in 2 TOPS NPU with running at the 4K resolution. So that model, again, as a comparison, if you're running it at like VGA, like the like 16:9 VGA, so 640 by 360, it's in the I think like 16 millisecond range. So it kind of scales up and down with size, but for Ocean, we didn't need the accelerator. But for other use cases where maybe you want to run 4K at 30 frames per second, that's where something like the Era 2 would come in.
Good. And actually, I think a similar question as well. have you explored using the IMX95 chip as well, or you think the IMX810 Plus is enough for these purposes?
Yeah, well, so this project, I mean, the 95 didn't exist when we started, and longevity is key. So, you know, for ADAS, it's very unlikely that we'd be looking at the 95, but as far as Au-Zone and the EdgeFirst stack, yes, we're actively working on the 95, and that'll be supported by the software stack and potentially a future Maven camera using the IMX95 as well.
Good, thanks. One more. So beyond maritime mapping, to what other use cases do you see this technology being applied?
Yep, so robotics for sure, and robotics adjacent. So I mentioned how we tie in very seamlessly into ROS. That's been kind of important principle for the system. So obviously robotics application that need this type of perception. And what I mean by robotic adjacent would be, you know, smart agriculture, industrial construction, where, you know, maybe it's not exactly a robot, much like ADAS is not exactly a robot, but you need a lot of the same type of perception. You know, maybe you need to see where people are in an environment. That was a big focus of the Raven platform, for example, mounting it to, you know, excavators, another piece of heavy equipment that deal with, you know, dusty environments where vision can fail, but we still need to be able to reliably detect where people are to make sure, you know, well, we don't run them over, basically.
All right, great. So yeah, it's a very versatile and also very modular, because you have the different, you know, from the platform all the way to the model, right? So
yeah, it could, I mean, with the model, it could be, you know, just about anything, you know, monitoring wildlife, putting it on a pole somewhere. It could be, you know, under 5 watts, you can have this as a solar powered platform. So it really, you know, imagination, data availability, what you're trying to do with it is, there's lots of places it could be used.
Great. All right. So Sebastian, with that, thank you so much for your time and for walking us through this wonderful presentation. Really excited about the future of the ocean cleanup project as well. I think it is a very nice project to keep an eye on. And thank you, the audience, as well, for joining and for asking the wonderful questions. We'll be sharing the recording and also the PDF. And yeah, Sebastian, looking forward to collaborate even closer together in the future. Thank you.
Great. Thank you very much.
Cheers. Bye-bye.
Bye.